system, improve medical decision-making, and inform public health policies. So let me go deep down. Why mathematics is preferred in life science? Yes, as you see the point, biological systems are among the most complex systems studied by science. They involve non-linear interactions, feedback mechanisms, and the variability across individuals and the population, of course. On the other hand, mathematics is preferred in life science because it offers precision in describing those complex relationships. Mathematical equations allows us to clearly define the relationship between biological variables. This precision is essentially when studying processes such as disease transmission, population growth, or biological interactions. Another major reason mathematics is preferred is its predictive capability. Using mathematical models, scientists can explore what may happen in the future under different conditions. This ability to predict outcome is invaluable in medicine, epidemiology, and environmental science, meteorology, whatever fields. They are very important. One of the most important advantage of mathematics in biological research is the ability to perform simulation, as you see. Simulation allows controlled simulations of biological phenomena. Simulations, in the other way, allows researchers, mathematicians to explore many scenarios without conducting costly or ethically challenging experiments. So mathematics also plays, as you see here, a central role in data analysis. So advanced in biotechnology have led to massive data sets, database, including genomic sequence, epidemiological records. So mathematics as well as statistical tools are essential for extracting those meaningful information from those huge data sets. So the other way we can see that mathematics supports evidence-based decision-making in medicine and public health. Decisions guided by mathematical analysis are more reliable as well as transparent. So mathematics as a universal language in biology, when we say, I can try to explain those points. Mathematics serves as a universal language that transcends disciplinary and cultural boundaries. Scientists from different backgrounds can communicate clearly through mathematical expressions and models. But if you consider like a text language, they may have different kind of meaning when we try to describe in our way on the when we send to the other way. But if it is a mathematical equation, it is a universal language. So easily we can understand. So by translating biological processes into equations, we researchers or scientists can compare results across studies or even across regions. So this shared language foster interdisciplinary collaborations and accelerate scientific discovery. So in this way, mathematics act as, we can say, a bridge connecting biology, medicine, even physics, computer science, and engineering. So my today's talk is just to enlighten an area of application of mathematics, a new area of modeling area in life science, and exactly to to show the beauty of this mathematics in those life sciences. So let me go deep down to mathematical modeling in a life science. So we can see here the types of the models and what does that mean, or in which cases that models will be applied. So mathematical modeling is one of the most powerful applications of mathematics in life science. A mathematical model is, as we know, it is a simplified representation of biological system designed to capture its essential behavior. So as I have said, different modeling approach are used depending on the biological equations. Let me say ordinary differential equation as an equations are commonly used to model population dynamics and the disease spread over time. Stochastic models are modeled to incorporate randomness and are particularly important in modeling infectious disease. So when we consider partial differential equations, it describes spatial processes. Yes, while agent-based model simulates the individual behavior of the one which are going to model. So according to our interest, according to the behavior of the population, even the number of the population, for small population, most of the time we use stochastic models, because if it is for big population, things will be very complex. So this is a kind of alignment, as I have said. So depending upon our aim, our goal, we can pick any of the approach. So later on, I will come to the area of the applications. Let me continue to enlighten another point: epidemiology and the disease modeling application and its contribution. As you see, some of my publications and other things are here. It is displayed. But when I come to the epidemiology, epidemiology is one of the most visible application of mathematical modeling in life science. Yes, mathematical models, as we know, it helps to track the spread of the disease, infectious disease, and it predicts future outbreaks, and also it helps to evaluate uh, intervention mechanisms, and also it helps to check different intervention mechanism in terms of cost, as well as their effectiveness. So those models are crucial for evaluating vaccination strategy as well as public intervention, as I have said. So during pandemic, COVID, when I say COVID pandemic, they provide essential guidelines or guidance for policymakers. I've been serving here in the Ethiopian context as chairman of task force in modeling, which is supported by the Minister of Health. Sorry, 1 minute. My kid. Okay. All right. Sorry for the interruption. You see, when we are at home, because here it is 6 p.m. So I'm at home. So let me continue. All right. So I was talking about the use of modeling during the pandemic. So researchers on COVID-19 at that time, not only in my context, but in all over the world, they clearly demonstrated how mathematical modeling saved lives. Even I can say saved life. The next slide, is it visible?
Yes, sir. You can continue, sir.
Hello?
Yes,
It's visible. It's visible.
Your slides are visible.
No. All right.
Please go ahead. Your slide.
What does it say? My slide.
Epidemiology and
We were
Can you tell me the title?
epidemiology and disease
Currently,
modeling.
your slide is on epidemiology and disease modeling. Can you hear me?
All right. Yeah, but I'm trying to change to the next slide. I'm unable to do that. That's why I'm trying.
You can stop sharing your screen and reshare.
Yeah.
Did you get that?
Yeah. 1 minute. 1 minute with screen. Let me share it again.
Perfect.
Okay. All right. Am I in on host pathogen interaction in the immunology?
Yes.
Yes, you are. Of course.
Yes. Thank you very much. Thank you very much. So, one of the application of modeling is in this area. As I have said, mathematics is not an easy subject, it's not an easy thing, but nowadays researchers are concentrated on this area or modeling on the host pathogen interaction in the immunology. So mathematics also plays a vital role on understanding immune system and immune response. So in this case, within host models describe interaction between this pathogen and the immune cells. So those models helps to explain why some infections are cleared quickly, while others become chronic. So in that case, we will try to investigate in the cell level, deep down to the cell level. So those models helps to explain the interaction of the immune cell, the pathogen, or a kind of vaccine, or if we have some kind of vaccine. So we can consider even that one. So they are also support the development of effective treatment strategies, especially when we develop drugs. They will help to develop effective treatment strategy drugs. So by combining mathematics with immunology, nowadays researchers gain deep insight into disease mechanisms or controlling mechanisms. So it is very important to see the beauty of mathematics deep down to the cell level. When I come to another area, drug resistance and the treatment optimizations. Of course, in the previous area, I already tried to display my publication in that area. So here, in case of drug resistance, nowadays it is a big issue in different areas. So of course, it is a global health challenge. So in order to help and to overcome this challenge, mathematical models helps to explain how resistance emerge and spread in the populations, even in the cell level as well. So by analyzing treatment strategies mathematically, researchers can design protocols that can minimize resistance. So these models have been applied successfully in like tuberculosis, even malaria, influencing treatment guidelines. So this is a current area. So we have to enlighten juniors or even senior researchers to concentrate in this area in order to overcome this growing global health challenge, drug resistance. The other area is ecology and evolutionary biology. As we know, in ecology, mathematics is essential for modeling population dynamics and species interactions. So we can see as in the 3 level, the key concept, predator prey. Then the next step, we can one step up into the evolutionary strategies, then the other one step big into the ecosystem applications. So predator prey models helps to explain fluctuations in the ecosystem, while evolutionary models describe genetic adaptations. So those tools are vital for conservations and environmental sustainability. So especially environmental change nowadays is a big concern. So uh,
We are back now, so you can continue.
Oh my God. Okay. I was talking, you see, you guys, I thought that you are already in. All right. So I have to share it again, or is it still my screen is visible? I have to share it again. Okay.
Yeah, we can see your screen now.
Okay. I was talking about ecology and evolutionary biology. Have you been together when I finish this slide?
You on this slide before it went up.
So anyway, I said that this, especially predator-prey models, it helps to explain fluctuation in the ecosystem, while about the evolutionary models describe the genetic adaptations. So they are very important to see the beauty of mathematics in this area. So the next area was, as you all of you know, that this is the machine learning, the AI. Now this generation is the AI generation. So it is very important deeply to explore mathematical modeling in this area. So mathematical modeling applications in the AI and the big data, especially AI in disease prediction and medical diagnostic, is very important to consider modeling in the in area of genomics and proteomics, especially as we know, big data analytics in genomics and the proteomics are very important. So in order to consider that one, modeling have replaceable contribution in this area. So the mathematical algorithms, power disease predictions, medical imaging, genomic analysis. So, or those approach support precision medicine and personalized even health cares. So, integrating the models like considering neural networks and the different approaches in our modeling technique is very crucial. So, especially being uh, uh, or creating a group from computer science, statistics, the one who is specialized in this area, and then integrating modeling modelers will make our research output really innovative and policy inputs. It will be a good policy input. So in general, when I come to impact of impacts on public health and the policy, so mathematics plays a critical role in public health, model guidance, resource allocations, and the intervention planning. So governments rely on mathematical predictions to manage pandemics and health crisis is crucial. So this ensures that policies are based on evidence rather than a kind of speculations, and it will become very cost effective, as well as we can alleviate different side effects by applying mathematical modeling. So I'm almost done. So I can say that bridging theory and experimentations, yes, mathematics connects theoretical ideas with experimental data. Models are validated using real-world observations. So these collaborations improves research efficiency and reduce experimental costs. So simulations also, it helps to refine hypotheses before even laboratory testing. So when I come to the challenge and the future directions of modeling, or in a broad way, mathematics. So its power, despite its power, mathematical modeling faces challenges such as data limitations, and the computational complexity is we can consider as a challenge. However, those challenges present opportunity for innovations. So future research will focus on multi-scale modeling. I can really appreciate, especially juniors, to consider on multi-scale modeling, on artificial intelligence, and a kind of improved data integrations. So really, I want to say, in conclusion, mathematics is a central pillar for modern life science. It enhances understanding, predictions, and decision making. Decision making, I can say, from molecular biology to global health. Mathematics shapes our ability to improve human and environmental well-being. Thank you very much for your attentions. I'm done. Thank you.
Thank you very much, Dr. Bilal. That was a beautiful presentation from Ethiopia. Thank you, East Africa. So once again, let's give him a round of applause. I don't know if there are questions from online participants. Questions from online participants? Questions? Yeah, okay, from the on-site. You have question? Anybody? One, only one.
Okay, there are people.
Okay,
Someone-
there's somebody. Osifo Agane, can you go ahead and ask your question?
All right, thank you very much. Good evening, everyone. So thank you for the opportunity, and thank you, Doc, for the insightful presentation. So you actually cited some challenges and future work. In the my question is relating to mathematical modeling, the aspect of precision medicine, which you mentioned. Uh, I don't know if is it possible that you can help share more light into that, because I think uh,
Who is this person? To come home on the call. How many?
Oh, can you hear me?
Yeah, no. Yes, now.
Oh,
Please go
okay.
ahead.
I'm so sorry. I thought I was unmuted before. Okay, thank you very much. So thank you for the lecture, sir, and thank you for the privilege to also join this meeting. My question is with respect to the aspect of precision medicine using a mathematical model. I would want to ask, like, how far has this aspect of research been, and also I'm still kind of new to that. That's what I'm asking, and how valuable can such predict precision like the mathematical model can be useful in precision medicine. And you mentioned some complications, some challenges which has to do with computational issues. So from your own perspective, sir, I don't know if there's any way you've been able to overcome such a challenge. So I don't know if you could share so that someone like me could gain some insights as I desire to grow in that uh line of research in the future. Thank you, sir.
Yeah, thank you very much. Okay. Yes. As I have said, when I try to explain the beauty of mathematics in life science, one of the thing is mathematics is preferred in life science because of it offers precision. Yes, describing complex relationship. Because in life science, when you try to explain complex relationship between cells, between very deep down complex things might not be easily understandable. So, but mathematical equations allows us to clearly define relationship between biological variables. So this precision is essential when studying processes such as I have said, cell level modeling or disease transmission or population growth or biochemical reactions. So, of course, when we come to the challenge in relating to precisions, especially when we have big data, error tolerance is not easy. It's not easy at that level. But the contribution of mathematics, as I've said, it is not replaceable in order to explain those complex phenomena of life science. So its contribution to precision in life science is great. It's great. Yes, this is what I want to explain. Thank you.
Okay, thank you. Thank you very much. You are fine with that.
All right, thank you, sir.
Any other participants? Okay, there is no. Is there anyone that has a question? Okay, Mogoju, please.
All right. Thank you, Professor, for the beautiful presentation. Can you hear me, please?
Yes, I'm hearing.
Okay. So my question is on the host pathogen interaction aspect of your work. I see that you've done quite some work in that area, and for me, I'm more familiar with the modeling at population level, and then we try to confront our model with data. We use incidence, prevalence data, and all sorts types of data. So I want to ask, for the host pathogen interactions, what types of data do you use? If I want to say I want to use I want to do a data-driven modeling work for the host pathogen, especially on the pathogen aspect, the within host aspect of the work. What type of data do you use for such modeling? Thank you.
All right. Yes. Your question is on the with the host modeling. Yeah. Shortage of data is a big challenge, but we have to try what we have, especially in the case of host. Within host modeling, the type of data that we use is laboratory data, especially the number of cells count, cell count, um, uh, the other when a drug is some amount of dose of drug is introduced to that individuals at one time, a number of pathogen which is eliminated due to that drug,
Okay.
and the other things, you know, a single pathogens when it introduced to the cell, number of cells, and effective number of infected number of cells, how many infected number of cells for that particular case, and the related data have to be there to make that modeling for policy outputs. So, of course, it depends upon your model objective. It depends upon the questions that you are going to address. For example, if your objective is in order to compare vaccination at the cell level, the capacity of the effectiveness of vaccination, one vaccine at the cell level. So you have to count the cell. You have to see the dose or whatever. It depends. So such kind of data is very important in order to do the validation of the model and to estimate the parameters. Thank you. If it gives sense for you.
Thank you. I think it's major experimental data when you are collected the viral loads, the parasite loads, individual of the not population level, serological data. Serological data.
Yes.
Serums, antibodies,
I think
that. So this kind of data can be used for viral dynamics or parasite dynamics within host. Immunological, immune systems or immune response models moving forward. Thank you very much. I don't know if there's any other question. Okay, thank you. In the absence of no other questions, we want to appreciate you for accepting our call, our invitation to give this talk. It happens that you will be the last webinarian for us in this year, 2025. So we appreciate you for coming, and we hope that when next we call on you, you are going to respond and we'll still enjoy more of your in-depth knowledge in the field of practical modeling of disease. Thank you, and greetings to everyone in Ethiopia. God bless you. Let's give you a round of applause.
Thank you, everyone. Ahead of times, I want to say Happy New Year because we might not meet.
Merry Christmas. Enjoy your holiday.
All right. Thank you. Bye.